Hi everyone and welcome to PrepFusion. I'm Anish and today we will be starting the lecture 15 of state space, right? So previously we studied controllability and its use cases, and we studied the diagonal form, basically how to directly see the state space representation and how to answer whether the system will be controllable or not. And then we found out few exceptions, that if my eigenvalues or poles are repeated, then we have to take in your mind few more rules, right? Keep in your mind few more rules, like if the eigenvalues are repeated, then there should be only one Jordan block with the repeated eigenvalues, right? As I explained in previous video also. We'll do a few questions from here also, we will understand. Also, on the last row of each Jordan block, the elements of the B matrix should be non-zero. Okay, so those were the basic two conditions that you need to keep in mind while solving with the help of Gilbert's test, right? Gilbert's test. So yeah, if you are not comfortable with that test, then you do with the Kalman's test. Test, because that is like just calculation, right? Nothing else. That is just calculation. So now in this lecture, what we will study? We will study the controllability from state diagram, basically continuing the previous lecture itself, and pole zero cancellation. So what happens to controllability of a system if there is some pole zero cancellation, and few questions obviously. Okay, so we'll try to end the controllability theory like here, and we'll try to start the observability in the next lecture. Let's see where it goes. So this is the first question. We have to check for controllability using Gilbert's test. I have given you this homework, right? So how do I check it? So first, like, what I'll do, I will first draw the state diagram. Okay, draw the state diagram of this one. So if I draw the state diagram, like anyways from here, right, you can see that simply if I apply the Gilbert's test, I see that I have repeated eigenvalues, right? I have repeated eigenvalues. So how many number of blocks we have? In the above of this repeated eigenvalue, there isn't a one, right? So this is the one block and this is another block. Okay, so I have two Jordan blocks, okay, for the same repeated eigenvalue. Then first condition isn't satisfied, then what will happen? Then this system, this state space representation won't be controllable. Okay, so yeah, from here just seeing the matrix I can say okay, but let's solve it using state diagram and understand it in more in-depth manner. Okay, so state diagram. Okay, so if I see the state diagram, right, so this is just basically like parallel decomposition. So I'll solve it like parallel only. So I'll have two components, one will go here and I will have two 1 bias terms, right? One bias here and another one here. This will also go 1 bias here. Okay, this will also go 1 bias here, and then like my output, right, I will add this to one output. So they are contained in parallel. Okay, they are contained in parallel. Okay, this is y, and like, okay, not this is not y, this is y. Okay, and this is 1, this is 1, this is basically 1, this is basically 2, okay, and this is basically 1, this is u. Okay, and okay, so why this is true? Okay, why this is true? Due to this one, right? Due to this one. So I'm assuming this is another state variable and this is one state variable. So this is the second state variable, right? So this is x2 of s. Okay, and like, what is the feedback here? Feedback here is simply -2, right? Okay, let me write this here. Feedback here is simply -2. Okay, so yeah, this is the basically the state diagram. Now can I say is this controllable or not? You might say that I'm available, like my input is available to, my input can go to both of the state variables. Then what is the issue? This system should be controllable, right? Why isn't this controllable? Why are you saying this isn't controllable? So for us to understand why it isn't controllable, let us solve for the transfer function of this one. Okay, so if I solve for the transfer function, right, so in case of parallel, you can see that simply this is 1 by s plus 2, okay, plus 2 by s plus 2, so it becomes 3 by s plus 2, right? So we get 3 by s plus 2. So this is only first order system, right? But still we are using two integrators. We are not using minimal set of state variables. That's why this isn't controllable, right? Okay, but like but you might say, then why is the pole zero cancellation here? I'm simply getting 3 by s plus 2, okay, by transfer function. Okay, we'll solve using both methods. From there also you understand. Okay, so my pole zero cancellation you will directly see when you solve using SFG, right? There you will see the pole zero cancellation. So yeah, let's solve using the SFG, okay, the Mason's gain formula, and from there you will understand, right? So I have this y of s over u of s, right? I have this y of s over u of s. Now I hope you remember the Mason's gain formula, right? So it's been a while. So in the bottom, what will come? Basically the determinant, right? Determinant, basically the loop gains. Like, okay, so how many loops I have? I have this loop and this loop. Any other loop do I have? No, this is like this is not along the path, and this is also not along the path, right? This is opposing the flow. So I have only two loops, and two of them are also non-touching, right? Okay, so I will have two terms. Okay, so first one will be one denominator, and then minus, then each individual loop gains. So this is the first loop gain, that is minus 2s, minus 2 by s, and then this is minus 2 by s again, minus 2 by s. Okay, and then what is it? Then we have this plus, and each loop gains will be multiplied. Basically the non-touching loop gains will be multiplied, right? So minus 2 by s times minus 2 by s is basically the denominator, right? And what is the numerator? The numerator, right? Numerator is basically now I have to calculate each forward path. So how many number of forward paths I have? This is the first forward path, and this is the second forward path, right? So first forward path, what is the gain of the forward path? It is 1 by s, right? So simply it is 1 by s. And what is the associated loop gain factor? The associated loop gain factor, it is gone, okay, and this is only here. Okay, so this is minus 2 by s, right? This is minus 2 by s. So the associated loop gain factor is minus 2 by s, and only as we have only one isolated loop, so there won't be another term like the non-touching ones, right? So this is gone. Okay, then we have another forward path. This has also the same loop gain basically, so it is 1 by s, and the terms will also be come out to be same, right? Because instead of here we're using here, but the difference here is this is 2 by s, right? So here this is a 2 by s, that is the only difference. So I also skip this part, miss this part. This will be 2 by s. Okay, so this is 1 minus what do you call, so this is 1 minus 2 by s, and this is and, right? Now we will simplify this equation, right? So if I simplify this equation, what do I get? So this common terms are same, right? So I can write 3 by s of 1 plus 2 by s. Okay, and what is this? This is 1 plus 4 by s plus 4 by s square. Okay, then what do I get? I multiply s square, right? I multiply s square, so this becomes 3s plus 2. Okay, then this becomes s square plus 4s plus 4, right? So yeah, now do we see any pole zero cancellation? So if I like if I see one thing, that what is s square plus 4s plus 4? It is s plus 2, right? So this is 3 into s plus 2 divided by s plus 2 into s plus 2. Okay, so here, right, here I can see this is s square 2 whole square, s plus 2 whole square. So here I see that there is some pole zero cancellation, right? There is some pole zero cancellation. So due to this pole zero cancellation, my system basically my state space representation won't be controllable, because it is not the canonical form. Basically we are not able to represent the system in the minimal form. Okay, So pole zero cancellation, I will write few points about pole zero cancellation later also. Pole zero cancellation happens. Why then what does this mean? We have not taken minimal set of state variables, right? Minimal set. Okay, why not minimal set? Because order of system is 1, but number of integrators that we are using, right, to represent in state diagram the system, we are using 2. Okay, that's why not minimal. Okay, that's why not minimal basically. So yeah, okay, so this is basically the concept of pole zero cancellation, right? Now, like as I was mentioning at the start also, I can solve this directly. Okay, but you will not see the pole zero cancellation, but you can get to the answer directly, the transfer function that I'm talking about. So these two are in parallel, right? These two are in parallel. So when things are in parallel, what happens to transfer function? So we have learned this multiple times, but when two blocks are in parallel, okay, this is h1 of s and this is h2 of s, then what happens? I will just draw this in rough. Okay, h2 of s, and this goes here and this goes here, and we have a adder. What does happen to the transfer function overall the system? So I can reduce this into one block of h1 plus h2. Okay, that will be my transfer function of the whole system, right? So basically that is what I will do. Okay, that is what basically I will do. So I will add the thing. So I'll first copy the state diagram. Things in parallel, right? Add the things in parallel at each forward path as they are in parallel, right? So how will I add? So basically, what is the transfer function of this one? Very easy only, right? It is simply 1 upon s plus 2. You can do it. It will come out as 1 upon s plus 2. Why 1 upon s plus 2? Because if you see, right, the forward path gain is 1 by s, and it doesn't have any loop gain factor with it, because only like this will be gone, right? This path will be gone, and if you simplify, you will get 1 plus 2. So you just apply Mason's gain in this forward path, and then you apply Mason's gain in this forward path. Okay, what do you see? The difference you will see is 2 upon s plus 2, right? So what will be my transfer function? My transfer function will be 3 upon s plus 2. Okay, from there you will not understand that there is a pole zero cancellation, but here you can understand that order of the system is 1, and I'm using 2 integrators for representing this system, right? So that's why I'm not using a minimal set. That's why my system won't be controllable. So this is basically the reason why this isn't controllable. And from Jordan block also, you can see Jordan block. Okay, we have 2 Jordan blocks, right? As I mentioned in the question itself, we have 2 Jordan blocks. So what was my matrix? This was 2 2 0 0, right? 2 2 0 0. So how many number of Jordan blocks I have? I have this Jordan block and this Jordan block. Okay, I have 2 Jordan blocks. Okay, 2 Jordan blocks. So for the same eigenvalue, hence like this is just a test, right? So we know system would be not controllable. I just wanted to explain it to why it isn't, right? Because we're not using minimal set of state variables. The state representation isn't controllable. Okay, so yeah, this was basically it for this question. Now let's go to the next question. So what does the next question say? So next question, right, tells us we have to check for controllability. Okay, I think I made a mistake in the spelling controllability. Just hold on a second. This happens. So okay, I have the spelling is correct. Controllability. Okay, I think this is, yeah. Okay, so we have to check for controllability using both Gilbert's test and Kalman's test for this particular like state space representation. So if I apply Gilbert's test, it is easy only, right? If I apply Gilbert's test, what do I see? I see that corresponding, like this itself is a Jordan block, and corresponding to the last row we have only one Jordan block for the repeated eigenvalues, and corresponding to the last row it is non-zero. So my system would be basically controllable. This time my system will be controllable. Now you might say, why? Here also I have repeated eigenvalues, right? Here also I will not get minimal set of state variables. Let's see, right? So let me draw the state diagram for this one. So how to draw the state diagram? So basically, right, if you have practiced enough, okay, for parallel decomposition, you can draw this directly. How? So how the state diagram will look? State diagram, right? So I will draw this now directly. The homework is like to understand how did I draw it without like I skipped few steps. So we have already done the Jordan block, like Jordan matrix previously. So I will draw this directly. So I have at least one transfer function s plus 2, right? And this is another one. Okay, this is one, this is one only, this is 1 by s again, and we have a feedback, right? We have feedback to -2. Okay, and this is u, and this gain is 1. Now u is also related with this x2 dot, okay, 2 times. So what I will do, I have already this one, right? I will take from here only. Okay, take from here only. This is the Jordan like block method. This is 2. Okay, then we start from here. Okay, again I will use another integrator, and this is -2, and from here I will take the output, right? This will be 1. Okay, this will be 1, and from here I will take the output, right? Okay, so this is what I will get, right? This is what I will get. So this is basically the state space representation. Now you might say, why is this that again I'm using 2 Jordan blocks and like 2 or like integrators, and why isn't this like why isn't this basically like minimal set, right? So here, right, if you calculate the transfer function for this one, you will get order 2, right? So how will my transfer function look like? It will be some parallel decomposition of this one, right? S plus 3, not s plus 3, s plus 2 plus b by s plus 2 whole square, right? So this time, right, this time there won't be any pole zero cancellation. There won't be any pole zero cancellation. Okay, it may so happen that there can be, if a and b are, we get something, or the pole zero cancellation is anyways there. Okay, so like, but if the homework is you calculate the transfer function. Okay, let me calculate the transfer function for you. Okay, so there won't be a pole zero cancellation. I will calculate the transfer function for you. You also calculate with me, and you check that are you getting order 2 or order 1. From there you will understand pole zero cancellation. Okay, so order, not always, this won't be order 2. Okay, and my, what do you say, my number of integrators is also 2, right? So I'm using a minimal set. Okay, now I have to just check whether it is controllable or not. Okay, that I will check using the Gilbert's test. Okay, that is of another matter. So let me first find the transfer function. Okay, so transfer function is si minus a inverse, okay, b, and we have a c in front, right? We have a c in front, right? So if I have a c in front, basically what I can do here is What is the value of c? C is 1 comma 1, right? C is 1 comma 1, 1 comma 1, and this is some value. Let's solve for this one. So this is like 2102. So this will be s minus 2 minus 1 0 s minus 2, and this is the whole inverse. And what is b? B is 1 2. B is 1 2. So what is this? Basically I will swap this two, okay, s minus 2 and s minus 2 and 1 and 0, right? So, and in the bottom I will have s minus 2 whole square, okay, and I have 1 2 here again, 1 2 here again. So okay, so this comes out to be simply okay, let me solve one of, like, this will be 1 by s plus s minus 2 and this will be 1 by s minus 2, but here, right, here I'll have 1 by s minus 2 whole square, so that whole square will cause this transfer function to become order 2. So yeah, 1 1, okay, this becomes 1 by s minus 2, 1 by s minus 2 whole square, okay, this becomes 0 1 by s minus 2, okay, and what is this? This is basically 1 comma 2, okay, 1 comma 2. So this is like simply 1 times 1 and 0, so this is 1 by s minus 2, and this is 1 times this and 1 times this one, so I get 1 minus 2 minus s square, 1 minus s minus 2 s square by 1 minus s minus 2, and this simply this one will be multiplied with 1 comma 2, right? So if I multiply with 1 comma 2, what do I get? I get this one, right? 1 by s minus 2 plus 1 by s minus 2 whole square plus 1 by s minus 2, okay. So what will be my final transfer function? So my final transfer function, right, uh, 1 by s minus 2 whole square, right? So yeah, this is basically my transfer function. So if you simplify this, you will see that there isn't any pole zero cancellation, but still let's do it. So this will be 2 minus s by 2 plus 1 divided by s minus 2. So yeah, there isn't any s minus 2 like cancellation, right? So no pole zero cancellation, and what is the difference? My input, right, my input can still see all of the state variables. This is one of the state variables, okay, and this is one of the state variables, right? This is the, let's say this is my x2 dot and this is my x1 dot, right? So my input can see both of the state variables, right? This one and this one, like this one also it can see, right? So that's why this will be controllable. The first case is, first it has to be minimal set, right? That is the first condition, obviously, for a state space representation. Then we'll go to the actual controllable definition. If it isn't minimal set, then what's the point of controllable, right? So yeah, from the state diagram you can understand this is minimal set. Now let's do the Gilbert test. Basically Gilbert test is easy only. So like let me copy this one. So how many number of Jordan blocks are there? Is it 2? I have 2 repeated blocks, and is it 2? No, right? It is only 1, right? So I check until the repeated eigenvalue, do I have 1 over or not? So the Jordan block will continue, right? Jordan block will continue. So I have only one Jordan block. and corresponding to the last row of the Jordan block, I have to check if the element of B is non-zero or not. So non-zero, hence controllable. Okay, so yeah, basically this is the main thing that we do test, right? So you can do Kalman's also. Does the question say to do Kalman's also? Okay, it says Kalman's also. So Kalman's is homework for you. If you do Kalman's, what you will see that this QC, right? Homework is for you. Homework Kalman's. Now just stop the video and do it now. Okay, so you cross check that this determinant of QC is not equals to 0, non-zero. It's coming non-zero, right? Okay, so yeah, this is basically what this is now, right? Now what we'll do, we'll understand a bit more of the Gilbert's test and why the test has rules like that one, right? The last two rules, right? That it should have only one Jordan block. Okay, I mean the repeated eigenvalues, it should have only one Jordan block, and the last row corresponding to the Jordan block should be non-zero for the B, right? So let's this is the representation, basically state space for a Jordan matrix, right? Jordan matrix. Now this is a Jordan block. Okay, now I will write this in terms of state space equation, and from there we'll derive. So if I write this in terms of state space equation, right? So this is x1 into lambda x1, this one plus b11 b, okay, this is not multiplied to this u1 plus b12 u2 lambda 1 x2 b21 u1 plus b22 u2, and x3 is the third space vector. It is lambda 2 x3 plus b31 u1 plus b32 u2. Okay, so this is basically my state vector, right? State vector. Now what should I do now? Right now, basically what was the rule saying? The rule says that if my last row corresponding to this Jordan block, this B matrix becomes 0, okay, all of them, then my system will not be controllable. Okay, so according to Gilbert's test, if b21 and b22 becomes 0, then system becomes uncontrollable. Okay, system becomes uncontrollable, right? So let's put b12 and b2 0. Then what does this become? Let me copy this equation. Let me zoom out a bit. Copy this equation. And if I make b21 and b22 0, then these terms goes to 0. Okay, these term goes to 0, and what happens is my this state variable, right, the second state variable isn't a function of input anymore. Okay, so my x2 becomes isolated from input. So x2 change in the state variable, second state variable becomes isolated from input. Hence I can't control this state variable, right? I won't be able to control this state variable. hence won't be able to control the future state of this state variable. Okay, so yeah, this is the main thing, right? Hence system becomes uncontrollable. Even if I can't control one of the state variables, then also as a whole the system becomes uncontrollable. So system okay, so yeah, this is the main thing. Okay, so yeah, this was one example. Now what is your like another example you can take is make like this is another Jordan block, right? This is one Jordan block and this is also another Jordan block. So you make the row corresponding to this b31 b30 and you will see again this like third state variable again will be isolated. Okay, from there also you can understand that the system will not be controllable. Now one thing, like the Gilbert's test tells us about these two rows. Now what if my b11 and b12 are 0? Gilbert's test doesn't tell about this row, right? The first row corresponding to Jordan block, it doesn't say. Let's see what happens. Now if b11 and b12 equals 0, okay, b12 equals 0, then what will happen is, will my system become uncontrollable? Let's see. So let me put b11 and b12 equals 0 in this equation, state equation. What does happen? So simply delete this one. Okay, and I have these, right? But okay, one thing I forgot to write in the state equation, sorry, really sorry, is that here I know you guys are screaming, like I have a x2 also, right? Sorry for the mistake. This will be a x2 bar also. Okay, I missed this. Okay, x2 bar, this will be also x2 bar, x2 bar. Okay, and here, so here also there will be some x2 bar, right? Plus x2 bar. Okay, so yeah, so this is x2 bar. So right, so basically my change in state is a function of the state variable itself and the second state variable. Now my second state variable is like change in second state variable is a function of this and also inputs, depending that b21 and b22 are not 0. So if they are non-zero, then this will be function of input, and by controlling this one I can control this one. So yeah, so we can't say about the controllability, can't comment about the controllability. Now will depend on, let me change the pen. Okay, will depend on b21 and b22, right? If they are also 0, then this will not be function of input also, then I won't be able to control the x1 also. So yeah, that's why the second last row, the last row of the Jordan block, okay, states that the B matrix has to be non-zero for that, right? Corresponding to the last row of the Jordan block. Okay, so yeah, that is very important. So yeah, that is basically the intuition basically behind the Gilbert's test rules. Okay, now let's do a few questions and from there we'll understand. So this is the first question. Okay, we have to check for the controllability of the system for which the transfer function is given. Okay, now right, when a transfer function is given, there is huge confusion, right? So when a transfer function is given, you have to check for controllability. So you have to write the state space representation. So how will you do it? Okay, so there are multiple decompositions of transfer function, right? One is the controllable canonical form, another is the observable canonical form, then there is diagonal decomposition, or you can say parallel decomposition, then there is cascade decomposition. So what should I write here is transfer function can be decomposed in multiple ways. Okay, as state space representation isn't unique. Maybe I have like told you this one, I think 1,000 times or at least 10,000 times in the whole chapter, right? State space representation in multiple ways as state space representation is not unique, right? So like you might say, what if I change it, like decompose it in terms of controllable canonical form, also known as the direct decomposition form, right? Direct decomposition, this is also direct decomposition, the OCF is also direct decomposition. So in this case, right, in this case my state space representation will always be controllable no matter what. Okay, my state space representation, okay, let me write this here. Controllable, right? Now just hold on a second to drink water. So right, if it is always controllable, so what's the point, right, of this question? So if I convert it into controllable canonical form, it will always be controllable. So is there any point? So that's why, like, generally in questions they will say, like, in what decomposition you have to do. If nothing is mentioned, right, then my suggestion would be to go with parallel decomposition, right? Okay, just hold on a second. Yeah, sorry for the interruption because I had a bit of, I don't know, throat issue, that's why. Okay, so yeah, we were studying about the controllable canonical form. Okay, now this one, right, will always be controllable. Now if I, like, we haven't studied about observability yet, but if I change this, like decompose this transfer function into observable canonical form, right, then here my like the state space representation would always be observable. So always be observable. Okay, but in case of parallel decomposition, we won't be able to tell. We have to check the matrix, right, representation. So if nothing is set, we'll always like do parallel decomposition on the transfer function. So if nothing is set, always do parallel decomposition of the transfer function, right? We always do parallel decomposition of the transfer function. Okay, so yeah, now let's do the parallel decomposition, right? So if I do the parallel decomposition, what is my transfer function? This one, right? So what I will do, I will do partial fraction again. So this one is my transfer function, so I will do parallel okay. So if I do parallel decomposition, what does this mean? This means that this will be divided into partial fraction, so this will be a by s plus 2 plus a by not a, b by s plus 3, and this is c by, okay, this is not equals to s plus 4. Okay, so yeah, so what I can do here is simply write, simply what will my a, again you put a like s equals to -2, so this one -2 plus 3, so 1, and this is 2, so 1 by 2 I get, so I get 1 by 2. So I will solve this a bit fast. S plus 2 plus, this is basically -3, so this is -1 and 1, and this is here. Okay, I made some mistake because I had to put -2 over here also. So if I put -2 over here, it becomes -1 for the previous case, right? So I have to multiply a minus also. So if you do the calculations, you will understand. So if I put -3 over here, what do I get? So if I put -3, so like this one will come, this will become -1, this one will become 1, and this one will become -2. So -2 by -1 basically, so it becomes 2 only, right? So we have 2 only, s plus 3, and what does this become? What does this c become? So c, right? So for c, so again I put -4 over here, so I get -1 over here, and I get -2 over here. Okay, so this becomes -2 into -1, so I get this as -3 by 2 basically. So I have -3 by 2, so this is -3 by 2. Okay, s plus 4, right? S plus 4. So now you know the deal, right? So basically we will solve this using each transfer function will like decompose using CCF, right? Controllable canonical form. So this CCF, okay, CCF, solve this using CCF, and this one also CCF, right? Each of them, and then connect them in parallel. Okay, so how will my state diagram look? So my state diagram, right, like it will have 3 integrators basically. Okay, one by s, and like the loop gain will be different for all 3. And this is this is this is right? So what does this one is connected like this one. So this one I am just doing it, we have done the procedure for this one, so I will not explain much. Okay, so I hope you are understanding what I am doing, right? So yeah, so side by side you should do it by yourself. Okay, so yeah, these, right, these terms, what does this mean? These are the y gains of the at the y side. At the u side, this the coefficient of s will be the gain of the u side. So u side has only one gain. Okay, and this is the y side basically, y of s, and this is the u of s. So this, right, this becomes minus of, so let me name the first one as minus of, this one 2, and this one -3 by 2. Okay, -3 by 2, minus of, and 2. Okay, so what does this become? The first one has s plus 2, so this will be simply s minus 2, and this one basically this one, right? This one is s plus 3, so this will be -3, and this one is s plus 4, this will be s minus 4, right? So yeah, this will be my state diagram. So from here I will have to write the state equation, and from there I will understand the controllability. Just wait one more second. Yeah, again sorry for the interruption. I don't know what is happening to my throat. So yeah, this was the state diagram. Now let's do the state space representation basically. So if I do the state space representation, so I have to remove this indicators, right, and write the state variables basically. So from here also I can see that the input is available to all of them. So this will be controllable. Okay, if even one of them wasn't available, then this wouldn't have been controllable. So from here itself I can say this is controllable, right? So okay, if I am reviewing this one I should remove. Okay, and this one I should remove, and this one I should remove, and this one is, let me name this as x1 dot, this is x1, x2 dot, x2, x3 dot, and this is x3. Okay, so I will directly write here the matrix x1, x2 dot, and x3 dot. Okay, and what is a is basically like the diagonal elements will be this one, right, eigenvalues. So I will not explain here everything, so you understand it for yourself, right, because everything has been explained in previous lecture very well. Okay, so x1, x2, x3, and my u, right, how I can write u. So this is how you will solve in exam also, very fast. Okay, starting you solve slow in when you're doing practice, but in exam you solve like this. Okay, that's why I'm showing the both sides, the slow side and the fast side. Okay, so u. Okay, and then y, what is y equals to? Y equals to this, right, minus of 2 and minus 3 by 2. So minus of 2 and minus 3 by 2. Okay, and this is equals to my x1, x2, x3 only. My x1, x2, x3 only, right? So this is what my y is equals to. Okay, so yeah, basically, right, so like from here also I can see my state, right, my input is available to the all the state. So this is known as state feedback. I can give state feedback to all of them, right? From this state variable I can get my state feedback to all of them. Hence system is controllable. And this is in state representation we say it like this, as this row is non-zero, as this, like this value element is non-zero, and this element is also non-zero. From here also you can say system is controllable. Not system, I mean, again I'm writing the same thing. Like we should write here as the state space representation is controllable. So again I should copy this one. Okay, it's difficult to copy this one, but I will still try. State space representation is controllable, right? So yeah, this is basically for this question. Now let's do another question, and let's see if I remove this, okay, or this one, then what happens to my controllability or observability. Observability I will do in the next lecture, but if I remove one of these links, right, then what happens? Now if I remove one of these links, then how my state space will become? My state space, right, instead of this being 1, this will become 0, right? This will become 0. So exactly that is what the next question is. Okay, we have to again check for controllability, and if this becomes 0, so we know the answer, it won't be controllable. Why? Because we won't be able to do the state feedback, right? We won't be able to get the state feedback. So I'll copy this one. Okay, copy this one. This is e of t actually, e of s. So this is in time domain. So t and y of t. Okay, let me copy this. So if that is 0, right, if that is 0, now, right, I won't be able to get feedback from this state, right? I won't be able to get feedback. no state feedback. Hence, what does this mean? This means basically my system is not controllable. Or from the row, right, from the this rule also, the Gilbert's test of diagonal matrix, you can understand we have done that already, that's why I'm not repeating it. So from here also you can see that this is 0, right, 0, hence not controllable. And like this is also no feedback, hence not controllable. Okay, so yeah, this was basically it. As like if we solve for this, right, if we solve for this, what will happen? There will be pole zero cancellation. There will be pole zero cancellation. How? Let's see. And if there is some pole zero cancellation, either the system will be controllable or not controllable or not observable. Okay, so yeah, let us see if there is pole zero cancellation or not. Okay, so you try to solve this. Okay, convert this again to the state space, right, I mean the Laplace domain. Okay, this one, and then find the transfer function for this one with this one link being broken down. Okay, if one link is being broken down, so if one link is broken down, then is there let's see if there is actually a pole zero cancellation. If I just remove this link, right, if there is actually a pole zero cancellation, so if I just remove this link, okay, now let us find the transfer function. So I will do this now directly without writing the SFG. Okay, without writing the SFG. So what will be my transfer function? So this will be one of the forward path and this will be the other forward path. This path is 0 only, so the path for the 0 path, okay, it will be 0 by this s plus 2. So s plus 2 plus 2 by s plus 3, 2 by s plus 3, and what is this? This is minus 3 by 2 by s plus 4. Minus 3 by 2 by s plus 4. Okay, so this is basically my transfer function becomes, right. Okay, you can check for SFG using Mason again, you will get this transfer function only. So what is the important thing here? So again what I will do is I will write 2 into s plus 4 minus 3 by 2 into s plus 3 divided by s plus 3 into s plus 4, right. So what will happen? I will have, like you might say, where is the other, like it is a second order transfer function, but I'm using 3 integrators, right, that's why this is not a minimal set. Okay, second order transfer function I'm getting, second order transfer function system, but using 3 integrators. Okay, using 3 integrators. So that's why this is not a minimal set. This is not a minimal set, right? So if this is not a minimal set, what is happening? There is basically a pole zero cancellation. So you might say I'm not seeing any pole zero cancellation, so I will like show you the pole zero cancellation basically. So where is the pole zero cancellation? Yeah, here, right. So multiply s plus 2 and s plus 2 in both numerator and denominator. You see there is pole zero cancellation. So I like showed it to you that there is some pole zero cancellation, right, pole zero cancellation. Okay, so yeah, this is what happening, right. That's why my system, for this reason, my system will be either uncontrollable or unobservable. Now like observable is in the next lecture, but still I will show you a bit of demo, right. What demo I will give you is basically, right, I will copy and paste this again. Okay, this one is this one. Okay, So if this is connected, that's fine, okay, but for some reason this is disconnected, right? This is disconnected. Then what will happen? Then, right, due to this I won't be able to see my output, right, from the state variables. Then system will become unobservable. But first what will happen? There will be pole zero cancellation. So first thing is there will be pole zero cancellation, and this pole zero will cancel only, right? Pole zero cancellation, okay. And due to this pole zero cancellation, basically due to this pole zero cancellation, my state space representation, okay, again I have to write this is painful, state space representation will be unobservable, right? We haven't studied unobservable yet. I will explain everything to you. So what does pole zero cancellation basically mean, right? So what does pole zero cancellation mean? So if there is, I have written it previously, I don't remember. So like I will write this here in formally, more better manner. Pole zero cancellation, right? Pole zero cancellation. So if there is some pole zero cancellation, right? If there is some pole zero cancellation, it means either the state space representation, again I have to write state space representation how many times I don't know, will be uncontrollable or unobservable. This unobservable part we'll see in the next lecture, and from here also you can see that the y can't see the state variable, right? Unobservable. But this depends, right? Like whether it will be uncontrollable or unobservable, it depends. It will be either of those two, okay, but it depends how the state variables are defined, okay. If at the output side this is 0, right, the link is broken, then it will be unobservable. If at the input side that link is broken, then it will be uncontrollable, right? So I have to understand the input can't reach the state variable. Depends on how the state variables are defined, you can say, or represented also, you can say, okay. So yeah, this is basically the main concept of pole zero, right? So you don't have to worry about pole zero until like there is some transfer function or something. If transfer function is given, you go for the diagonal form, okay, because CCF form you go, you will get controllable only, like OCF form you go, you get observable only, right? So diagonal form you go and then check, but they will most probably tell you the like form, right? And like this pole zero cancellation will happen like when they will give some state space representation, and you will see that at the, if you find the transfer function, right, the like order is less, right? The order of the matrix is, let's say, what was the order of the matrix here? It was 3/8, right? It was 3. But as I can see, when I calculate my final transfer function, I am getting order as only 2, right? I don't need 3x3 matrix, I only need 2x2 matrix, okay. You will see that, right? You will check after finding the transfer function, you will see that one of pole zero are cancelling each other out, and I have only I only require 2 state variable, but this is taking 3 state variables. So yeah, that's why the system will not be controllable, okay. So yeah, that is the main concept about the pole zero cancellation. So if there is some pole zero cancellation, that means either the state space representation will be uncontrollable or unobservable, okay, but it depends how the state variables are defined. If at the output the link is broken like this one, then it will be unobservable, okay. We'll know about unobservable in the next lecture. And if at the input the link is broken, then it will be uncontrollable, as this input can't see the state variable, right? It can't take the state feedback, that's why, okay. So yeah, this was basically it for pole zero cancellation. Now let's solve few questions, right? So this is the first question. So this is a similar question as the example that I took at the start of controllability, right? That like this is a gate 2021 question. The question has stated that the state space representation of a first order system is given like this one. So this is a 1 cross 1 first order system. So this is a 1 cross 1 matrix where x is the state variable and u is the controlled input. So u is the controlled input, y is the controlled output. Let u equals to minus kx. So u is taking some state feedback from from the state, right, from the state itself, right? So u becomes minus kx, be the controller. It will be the control, basically the control equation. Don't need to read all this, okay? I mean, you can read this, but this is not important. The important part is where k is a controller gain, and to place a closed loop pole at -2. So can you tell me where is the pole right now? Okay, tell me where is the pole of this state space representation right now. What is the eigenvalue? Eigenvalue is -1, right? Eigenvalue is -1. So why do I need to place the pole? I need to place the pole at -2. So I need to shift the pole from -1 to -2. So how I will do that? So basically, right, use that state feedback equation. So just replace this x u with minus kx and then solve, right? Then we have to find the eigenvalue. So what is my x dot of t? X dot of t equals to simply minus x plus u, right? So we'll replace x with kx, okay? So this becomes k minus 1 into x, okay? So this is my x dot. So my eigenvalues, right? Okay, one more thing, this was okay, this was minus kx actually, okay, sorry. So like you can either calculate transfer function. So like I told it directly right there, but here I will tell you in brief also. So okay, I will tell you two methods. So one method will be here, basically transfer function method. So what is my transfer function method? It is basically c into si minus a inverse into b, right? Now what is my not in this case, okay, not in this case, normal transfer function, what will be this? So b, right, b is 1 only, okay, and this what is this? C is 1 only. So this becomes 1 and 1, and si minus a inverse is just like inverse of a single element, okay? This is s minus of, like I'm taking the transfer function of this one, right? Transfer function of this one. Transfer function won't change, right? It will remain constant for a system, right? It will remain constant, okay? Obviously, like it is with respect to t upon u, okay? T upon u, y upon u, okay? Here, like I am replacing the y like this one, but I will explain it to you. Just wait for a second. So it becomes this s minus a, and what is a? A is my -1, right? A is my -1. So minus of -1 times 1 1, right? So this becomes, this is inverse, so this becomes s plus 1, okay? So this becomes s plus 1, right? So yeah, this is what my transfer function is now, right? Like for poles to shift, right, the main thing is like they have done one thing wrong, okay? One thing they have gone wrong is these are written is u should be equals to minus kx plus r of t also. As this r of t would have remained here, right? R of t would have remained here, then we wouldn't have an issue. So that thing they have done wrong, okay? So but you don't need to like too much get confused. So this is one way, and here you can see the pole is at -1. So from -1 I have to shift it to -2, j omega and sigma. So this is my -1 pole and this is my -2. So I have to shift it like this one, right? So basically, what is this? What is the eigenvalue of this one, right? What is the eigenvalue of this one? -1. So like this one also you can calculate that eigenvalue of this one is lambda. This one is -1, right? So lambda this one -1, then what will be the pole? Pole will be simply equals to lambda, which is -1. So it's simple like that only. You don't need to do this much. Here also, what is the eigenvalue of this one? Eigenvalue of this one is minus only single element, right? That element will itself be the eigenvalue. So minus k -1, okay? And this will be pole, new pole basically. Okay, this will be a new pole. So basically, right? Basically my new pole is equals to -2 and this is minus k minus 1, so k becomes 1. So this is my answer. Okay, this is my answer. So k will be 1. So yeah, there is some mistake in the question. Basically, like this one, you write u should be equals to minus kx plus r of t. There is also an r of a, right? So sometimes, yeah, a bit of errors may happen, but the thing that it wanted to found out was, can you find the value of k? Okay, and can you use the concept of eigenvalues and directly calculate the transformation? So yeah, that is important. So yeah, this is the basically end of my state controllability. Basically, now one more very small topic is left. The topic is output controllability. Now this is not that important, and this may not, this doesn't come in exam, but just to completely study the controllability, we'll study it. So what do we mean by output controllability? So we want to control the output with our input. What were we doing previously? We were controlling the state variables with the input, right? Now we want to control output with input, right? So that is what we want to do. Okay, so what does my x dot becomes? So my x dot, right, x dot will become x plus bu, right? X dot will become my x plus bu. Okay, and what will my like, this is my just my state space equations. This is cx, y equals to cx, and d we ignore. Now this output, right, will be controlled by this input. So right, so how do I do that? How do I do that? So now again I will give you a bit of intuition of how that like proof came. Okay, why did that equation came? Okay, and what is the rules? Why did that rule came? Okay, I will give you a bit of intuition, but I will not do the complete proof, right? I'll just give you an overview, so as it will just waste time, but because this is not that important. So what is my y? So my y of t, right, in time domain, what is my y of t in time domain? Y of t in time domain is c into Laplace inverse of 5s into b into u of s. Okay, so this is my y of t. So now, right, again I will do that same thing. Okay, same proof, right? So what I will assume is, like, assume initial conditions to be 0. Initial conditions to be 0, then my x of 0, right, x of 0 will be 0 simply. Then what will my x of t become? X of t will become e raised to power at convolution, not convolution, actually I have a b also, because b is a not a function of s, so b I can take out. Okay, b I can take out, but I have to follow the like order, right? B is after this e raised to power at. E raised to power at I will understand, right? I just took the Laplace inverse of this. And what is the Laplace inverse of state transition matrix? It is basically this, right? State transition matrix in time domain, which is e raised to power at. I will understand it. So this is also known as state transition matrix. Sorry, this is known as state resolvent matrix, and this is known as state transition matrix. Doesn't matter what you call them. Okay, in gate examination you have to just solve the question. That is more important. But obviously if you go to interview and something, so it may matter. That's why I'm giving you all the theoretical points also, and how to crack the exam also. Both things you have to have good knowledge, right? So e raised to power at b times this u of t, right? Convolution e of t, not times convolution of e of t. Okay, u of t is not the unit step, it is the input, right? It is the input. So again, how can I write it? This is 0 to t, like e raised to power at. Again, right, the convolution formula, if you don't know, it's totally fine, because this will be taught to you in signal and system. Just for the people who know a bit of convolution, they can understand this proof. If you don't know, don't need to stress, because this proof will come nowhere, not even in your interviews, nowhere. Just after you learn convolution, right, you come back to here and see, then it should be introduction. Oh, it was like this one. Okay, that's how we solve it. Okay, that you can do. Okay, right? Else you don't have to stress that much, like if you don't understand the proof, right? So u of t d tau, right? So convolution formula is like this one. Okay, so what will my y of t become? My y of t will be c, basically this c times this one, right? Because c is on the outside. Now what I do, again I will replace this e raised to power e minus t minus tau to this series formula, right? Series power formula. And if I break it down to series power formula, okay, that is not important, that will take time. So my y of t will become this cb, then cab, and like this first term, second, then c a square b, and going on until c a raised to power n minus b. Okay, n minus b. Okay, so yeah, this is basically what my o of t is. Okay, this is basically what my o of t is. So what is my what is my like it may be some function, like it is multiplied with some function of t because there is some integration, right? So this is the main thing, and it is multiplied by some function of t. Okay, let's say it is beta naught t. Okay, then this is beta 1t, and this is going on until beta n minus 1 t, right? So yeah, so for output controllability, what condition needs to be matched, right? So the condition that needs to be matched is basically, right, this matrix is not n cross n. Why? Because this, right, this is some p cross n, and this is some n cross m, right? So we get p cross m matrix, right? This is not m cross n. So what you have to keep in mind is, so I can simplify this one also. So this, let me name this as QCO. Okay, controllable output matrix. Okay, so my QCO, right, QCO will be, if I can take C common. Okay, as it is pre-multiplied, right, I can take C common. Okay, what do you have? B, and this is AB, and this is A square B, and it is going on until A minus N B, right? Okay, so I can write my this QCO, okay, as C times the QC matrix, the controllable matrix, right? So that what I can write is here. So what will the final order? The order of this one, right, it will be some P cross N. Why? Because the order of this one is P cross N. I hope you are understanding, right? I'm just writing the matrix orders. This is the number of outputs, and this is the number of state, right? Order of the system basically. Okay, so this has already taught in like the first few lectures, so you should have like crystal clear concept in this. So this is P cross N. Okay, now this is getting multiplied with a matrix of n cross n. This one we know, right? This is n cross n, and we find the determinant. So this is C times QC. So we will get, okay, if let's say for example, generally my output is like P is 1 only, number of outputs is 1 only. So what does this become? This, right, this becomes like a row matrix only, right? QCO becomes a row matrix. Okay, row matrix. Okay, row matrix. Now, right, now what is the condition? What is the condition for my this state space representation to be output observable? Okay, the condition is that just wait, condition for output observable. Okay, condition is my QCO matrix, right? QCO matrix should have full row rank. Okay, my QCO matrix should have a full row rank. Okay, what do I mean by full row rank? So let's say I have a row matrix. Okay, QCO, let's say it's like n is 3. Okay, so I'll have number of columns as 3, 1 0 1. So this has full row rank, right? How? What is the rank of this? Rank of this is 1, right? Rank of this is 1. Okay, because like when we calculate the rank, right, when we calculate the rank is the minimum of number of rows or column. Okay, minimum of number of rows and column. We study this in mathematics. If you don't understand, that's okay, because this output observability isn't like, will not come in gate. Okay, but just to understand the concept, you study mathematics. Okay, I will teach you mathematics. After that you will understand this. Okay, so I will not teach again that rank thing. Okay, matrix, it comes under mathematics part. So this rank is 1. So what does full row mean? Full row rank means that my rank should be equals to the number of rows. Okay, rank equals to number of rows, right? So yeah, this is the basically main thing about full row rank. Okay, so now if how can it be not full row? So let's say I have a matrix like this one. Okay, let's say QCO. Okay, this is QCO, right? Yeah, QCO. Let's say this is 101 and 202. So is this full row rank? No, right? Why? Because these two rows are dependent on each other. So only I have one independent row. So my rank will be 1. Okay, rank will be 1, and this is not a full row rank, right? Full row rank. Okay, so in this case my output won't be observable. Okay, so this was basically the example for observability. If it is full row rank, it will be observable, and if it isn't, then it isn't observable. So did I write it? Condition for observability. Okay, output observable. Okay, this is the main thing you have to understand. Okay, so yeah, now let's understand a few key points. First key point is that output controllability and state controllability are totally independent from each other. They don't have any relation, right? They don't have any relation. So like if your state is controllable, then it doesn't mean that your output will be controllable, or vice versa. Okay, so they don't have any relation, so don't get confused. And by default, I just taught you the concept of output what do you say, controllability, but it isn't that important, so just you can skip it. Okay, just to teach few guys, okay, if they want to really are interested. So by default, if nothing is mentioned, we will always find state controllability, that we have been studying up till now for the 3 lectures, right? That we have been studying. So always find our state controllability. For some reason, some wild reason, they may ask you output controllability, then you use this one, right? So rank, okay, row matrix, all this we'll understand in mathematics. But even if you got a basic idea, right, that what does this rank mean? Basically, right, the full row means number of rows, okay, and rank means how many rows or columns are dependent on each other, right? Here, right, what do you see, that this is twice of this one. Okay, this is twice of this one. So what will be my rank? How many independent columns or rows are present in my matrix? That is basically my rank, right? So the minimum of that one will be my rank. So here, right, what I see is only one independent row is present. Okay, this other row is the dependent on this one. If I multiply 2 with this one, I will get this one, right? And for column, what I see, 1 2 0 0 1 1 2. So I see 2 independent columns and 1 independent rows. Okay, so I will choose the minimum. Rank is the minimum of the independent rows and columns, so rank will be 1 in this case. Okay, I just gave you a brief example. Okay, in more brief manner we will study in engineering mathematics. Okay, that will come soon. So yeah, that is QCO basically, and that is rank. Okay, for this case rank is 1. So here my number of rows is 2, but rank is 1. Hence my matrix won't be my output won't be observable. Okay, output won't be observable. So yeah, this was basically the case. Now yeah, the key point I gave you. Okay, now we'll do one question. So what is the question? Check for state and output controllability of the system for the state space representation, right? So it is check for state and output controllability, right? For state, it is easy. What I can see, I have repeated eigenvalues. Okay, and this is like a Jordan block. Okay, this is one Jordan block and this is another Jordan block. So what I can see, the last row corresponding to the Jordan block is non-zero. That is fine. Okay, check 1. Check 2 is row corresponding to this Jordan block, it is 0. Okay, then my output won't be like control sorry, not output, my state variable won't be controllable, right? So using Gilbert's test, using Gilbert's test, controllable. Now what is your task? Your task is to verify this using what? Using Kalman's test, right? You verify this using Kalman's test, right? So yeah, that is your task. Okay, so few things you have to do also. You have to practice more calculations in gate. The calculation should be very fast. Okay, so yeah, did you calculate and check if mod of QC is equals to 0 or not? What? Check mod of QC. What is mod of QC, right? What is mod of QC, right? So yeah, now right now let's calculate the output controllability. So how will I calculate? So what I have to do is multiply this matrix, right? This is the QCO. Okay, do it like this one, CAB. Okay, then this is CAB, then this is CA square B, third order, right? Like third order, so I have to do it 3 times, right? So what is CB? Right? CB is simple only. So this is 1 times 0, so this becomes 0. 0 times 4, 0. 1 times 0, 0. So it is 0 plus 0 plus 0, 0. Okay, then we have CAB. So okay, this is 0 only, so I should write this as 0. 0. Okay, and what is CAB? Now CAB is difficult. We have to first calculate AB, then we can do. Okay, or we can calculate the what do you say, C into A. So if I calculate the C into A, what is it? C into A, what is it? This is 1 0 1, and this is right. This is minus 2 0 0. Okay, so we get minus 2 only. Okay, like this one, right? 1 times minus 2, then we get minus 2, and plus 0 into 0 plus 1 into 0, 0 only. So 0. So now 1 times this one, and 0 times this one, and 1 times this one, so we get 1 only. And 1 times 0, 0 times 0, and 1 times minus 3, so I get minus 3 only, right? Now I have to multiply with B. So CAB, what I will get? So this is minus 2 1 minus 3. Okay, basically, right, when I see, it will be only one single column matrix. Okay, one single row matrix. For this case to be output observable, one of the element at least has to be non-zero. Okay, for when my output number of outputs is 1, so that thing you can remember. Generally my number of outputs is 1, then how will my rank be 1? If at least one of the elements here is non-zero. Okay, then my rank will be 1. If all of the elements are 0, then my rank will be 0. Okay, because it is covering null space. Okay, null space. That's why this, if you don't understand, we'll study in mathematics, right? Don't worry. So this is minus 2 1 minus 3. Okay, and we are multiplying by B. What is B? B is 0 4 0, right? 0 4 0. This becomes minus 2 into 0, 1 times 4, so this becomes 4 only, right? CAB becomes 4 only. Okay, CAB becomes 4 only. So I can stop here, right? I can stop here, that at least one element is non-zero, so my output will be observable with the input. Okay, so I can stop here, but still I can go on, right? So I will go on fully. Okay, we can stop here. I will write we can stop here. Okay, and this is A square B. So what is A square B? No, so what is C? Okay, CA square I will do again. I will do CA square basically. CA square, what is CA square? CA square is basically this minus 2 1 3, right, times A basically. So A is this one. So what is this? Again we'll get a row matrix. This is minus 2 times minus 2, 4 0 0. So this becomes 4, and this is minus 2 times minus 2 and 0, so this becomes minus 4. Okay, and this becomes 0 0, and this becomes minus 9. Okay, so this becomes minus 9. So this is 4 minus 9 minus 9. So my QCO, right? Okay, again I have to multiply this with B also. So if I multiply this with b, okay, ca square times b, okay, what is ca square times b? C square times b is 040 basically. So again what do we get? We get minus 16 over here. So first element is 0 gives you, and the next element is 4, and this is minus 16. So what is the rank here, right? Rank is 1, okay, rank is 1, okay. So like number of independent columns is also 1, because this 4 is dependent on this one and this one, okay, because if I multiply 0 with this one, I'll get this one, right? So number of independent column is also 1, number of independent row is 1. We have only one row, but all of them are non-zero, okay. So what is the short trick? Short trick is for like single output if one, like only if all the, okay, let me change the color, elements are 0, then the state space representation, the state space, okay, let me write this in next page actually. Representation basically will not be output controllable, okay. So yeah, this is not that important. If it feels overwhelmed to you, don't worry, you don't have to remember all this, okay. This is not that important, you can skip this part, okay, just for the people who really want to study so much, okay. So single output system, so I will write here also in the name of the topic also that this is not important, okay, not important for gate, not important. So if you want to skip, you can skip, don't worry, okay, but I have to teach everything, right? So that's why, okay. So not important, so that's why what I told, that we have to have a full row matrix. I explained everything to you. So in the next lecture, right, this lecture has already gone long, so I will give you a revision of the this lecture in the next lecture, okay. Thank you for watching. We'll start with basically controllability. Yeah, thank you for watching.